Close your eyes. Take a deep breath. Everything you call real is right now being silently processed by your brain. The texture of the pillow, the sound of my voice, the feeling of your body resting on the bed. But what if all of this is just one layer, one version among many? At the beginning of this journey through the concept of the multiverse, we start from the most fundamental point. What does it mean to exist? What do we call reality? And how do we know ours is the only one? For millennia, humanity believed it lived at the center of the universe, both physically and spiritually. From Aristotle to the Middle Ages, the world was seen as a hierarchical, finite, enclosed structure. But with Galileo, Copernicus, and Newton, that idea collapsed. The universe came to be viewed as a vast, mechanical, impersonal space. Centuries later, with Einstein and the theory of general relativity, we realized that space and time are not absolute, but rather flexible fabrics that bend, expand, and can even merge, creating a dynamic stage where reality transforms depending on who observes it. The notion of world was no longer fixed, but dependent on perspective and the structure of the universe itself. But the greatest shake-up in our idea of reality would come with quantum mechanics. In the early 20th century, as physicists like Niels Bohr and Werner Heisenberg studied the behavior of subatomic particles, they discovered something unsettling. The fundamental components of matter don't obey classical laws. A particle can be in two places at the same time. An electron only chooses a state when someone observes it. This feature, called quantum superposition, raises a disturbing question. Does the real universe depend on observation? And if so, are there other outcomes, other realities coexisting with ours where different choices were made? The multiverse hypothesis begins here, at the boundary between what we can observe and what mathematics allows us to conceive. And in this case, mathematics is not alone. It's supported by experiments showing, for instance, that one electron's behavior in a double-slit experiment changes when the experiment is observed, suggesting that the very act of seeing alters the system's state. In 1957, physicist Hugh Everett III proposed a radical solution to this ambiguity. All possibilities happen, but in separate universes. This gave rise to the many worlds interpretation of quantum mechanics, a model accepted by part of the scientific community, including physicist Sean Carroll, Caltech, who openly defends the idea that multiple versions of the universe coexist, each reflecting a different chain of events. But let's return to the original question. What is the world? Is it what we can touch, measure, feel? For modern physics, reality is a system of laws that manifests differently depending on the level of observation. There is the classical reality of falling apples and moving cars, and there is the quantum reality, where particles tunnel through barriers, exist in multiple states and affect one another even when separated by light years, a phenomenon known as quantum entanglement, experimentally confirmed in 2022 with the Nobel Prize awarded to Alain Aspect, John Clauser, and Anton Zeilinger, who demonstrated that entangled particles behave as a single system regardless of the distance between them. This leads us to an even deeper point. Is reality local or global? Deterministic or probabilistic? Limited or infinite? According to cosmologist Max Tegmark, MIT, not only do multiple universes exist, but each represents a more possible mathematical structure, forming what he calls Level 4 multiverse. For Tegmark, mathematics is more than a language. It is the substance of reality itself. As you fall asleep with this question in your ears, you are invited to accept that reality may not be a place, but rather a condition, a projection of something deeper, vaster, and stranger than we can imagine. The idea of a single world may just be an adaptive illusion, a way for the brain to simplify the incomprehensible. Like a fish unaware of the entire ocean, we see only the illuminated part of reality, and it's just a tiny fraction. What we call the world might perhaps be just a bubble floating in a cosmic sea, and within this bubble right now, you are about to drift into sleep, with the universe expanding around you, silently. Imagine yourself gently floating, eyes closed in an endless expanse. The sound of my voice is only a distant echo, and all that exists is the darkness speckled with faint lights, stars, galaxies, nebulas. But is what we see everything there is? The truth is that the observable universe is only a small fraction of what might be out there, and understanding this limit is essential to exploring the possibility of other worlds, other lands, parallel ones. The observable universe is, by definition, the region of the cosmos from which light has had time to reach us since the Big Bang. Since the universe is about 8 billion years old, it would be tempting to think that the radius of this visible sphere is also 13.8 billion light-years. But it's not that simple, because space has been expanding since the dawn of time and accelerating. The actual distance between us and the farthest galaxies is much greater. Current estimates based on standard cosmological models like LCDM, lambda cold dark matter, suggest that the radius of the observable universe is approximately 46.5 billion light-years. This means the total observable diameter is about 93 billion light-years. And beyond that, is there something more? Scientists believe so, and it's not blind belief. It's a logical extrapolation based on the isotropy of the universe. The idea that the cosmos is on large scales, uniform in all directions. If it is homogeneous and isotropic, as observations of the key cosmic microwave background, CMB suggest, recorded by missions like WEMAP and Planck, then it's reasonable to suppose the universe extends far beyond what we can see, perhaps infinitely. But the limit of what we can observe is a kind of cosmic horizon, much like the horizon of a ship at sea. It's not an absolute end. It's simply the point up to which light has had time to reach us. What lies beyond that limit still exists, but the light it emitted hasn't had time to arrive here yet, and perhaps never will, due to the current accelerated expansion of the universe, a phenomenon associated with dark energy, a mysterious form of energy that makes up about 68% of the total energy content of the cosmos, and which is causing space to stretch faster and faster. For many scientists, this means there are entire regions of the universe that have become causally disconnected from ours. That is, regions we will never be able to observe or interact with. For us, they are like other universes, even though they are part of the same fabric of space-time. This is where ideas about the inflationary multiverse cause gain strength. If the universe is vastly larger than we can see, and if cosmic inflation, a super rapid expansion in the first billionths of a second after the Big Bang, occurred unevenly, then each inflationary bubble could have created a universe with distinct properties, forever separated by distances no signal could ever cross. Physicist Charles Alan Guth, who proposed the theory of cosmic inflation in the 1980s, was one of the first to suggest that this expansion could be eternal, creating a scenario known as eternal chaotic inflation. In this model, our universe is just a bubble within a vast sea of universes, each with its own physical laws, fundamental values and dimensions, and all of it is beyond our reach, veiled by what we call the cosmological horizon. It's important to emphasize that none of this is mystical speculation. These ideas arise from equations, simulations, and empirical data. They're based on observations like the large-scale distribution of galaxies, the cosmic background radiation, and the behavior of the universe's expansion. Scientists like Andre Linde, Stanford, one of the architects of the modern inflationary model, argue that the existence of multiple universes is not only possible, it is probable. But for you who is now relaxing, perhaps the most comforting image is this. You live on a small island of light, surrounded by a vast and unknown ocean. Everything you've ever seen, heard, touched, or known is inside that luminous bubble. But beyond it, there may be billions of other worlds too far away to see, but not too far to be imagined. And in that ocean of possibilities, where each point may contain an entire cosmos, the silence of the night takes on a new meaning. Because perhaps as you sleep, infinite versions of you are also falling asleep, in other renditions of this same reality, each with its own stars, planets, and stories, and you are only beginning to dream of them. Close your eyes, breathe slowly. Imagine that your reality, your life, your thoughts, are just one of many possible expressions of what the universe could be. The idea that we live in one universe among many might sound like science fiction, but over the last century, it has emerged as a mathematically plausible, philosophically intriguing, and scientifically inevitable possibility in some models. The multiverse didn't arise from fantasy. It is, in fact, a logical consequence of some of the most widely accepted theories in modern physics. To understand how this notion was born, we need to go back to the zero moment of creation, the Big Bang. The Big Bang theory is not mere speculation. It's a model strongly supported by evidence such as the cosmic microwave background, the abundance of light elements like helium and hydrogen, and the recession of galaxies, first measured by Edwin Hubble. But even this theory left some questions unanswered. Why is the universe so uniform in all directions? Why is it so flat? What happened in the very first moments of time? To answer these questions, physicist Alan Guth proposed the theory of cosmic inflation in the 1980s. According to this theory, in the first 10-35 seconds after the Big Bang, the universe underwent an exponential expansion, growing more in a fraction of a second than it would over billions of years. This would explain the cosmos's homogeneity and isotropy. But shortly after this inflationary burst, other physicists, like Andre Linde, saw something even deeper, that inflation might be eternal. The so-called chaotic eternal inflation proposes that while some regions of space stop inflating and become universes like ours, others continue to expand forever, generating an infinite number of bubbles, each with its own physical laws. Each bubble is a universe. Each bubble is a possibility. Each bubble a reality. This idea may sound metaphysical, but it arises directly from quantum models applied to inflationary cosmology. It's not a belief, it's a consequence. Scientists like Brian Greene, author of The Hidden Reality, explain that there are many types of multiverses possible, each arising from a different theory. The inflationary multiverse, the quantum multiverse, the brain multiverse from string theory, the computational multiverse, all are mathematically viable and to some extent expected. Another key origin of the multiverse idea lies in quantum mechanics, specifically in the already mentioned many worlds interpretation by Hugh Everett III from 1957. Faced with the famous dilemma of wave function collapse, where a particle only chooses a state when observed, Everett proposed something radical. What if all outcomes happen simultaneously, but in separate universes? If in one world the particle goes left, in another it goes right, and both worlds continue to exist, diverging at every moment. This vision was ignored for decades, considered too bold. But today, researchers from institutions like Caltech and Oxford University admit that this interpretation not only resolves certain quantum paradoxes, but is also mathematically elegant and consistent with Schrödinger's equations. There's no need to invoke a mysterious collapse. One simply accepts that the universe is constantly branching, like an infinite tree of possibilities. Modern physics, then, offers us multiple paths to the multiverse, each born from a different branch of science. Cosmology, quantum theory, relativity, string theory. None of these paths were designed to create the idea of a multiverse, but all of them ended up there. And now, as you hear this, you may wonder, why haven't we ever seen another universe? The answer lies in causality and the separation of spaces. Each universe may be so distant or so disconnected from our space-time that we'll never be able to interact with it. Or perhaps our own universe is inside another, like a bubble within a cosmic foam, a concept supported by theorists like Leonard Susskind and Raphael Bousso in the so-called string theory landscape, which allows for 2,500 possible solutions to the fundamental equations of the cosmos. In light of this, the idea that there is only one world starts to feel limited, not because we want others to exist, but because the equations point that way. And just as we once discovered that Earth was not the center of the universe, and later that the Sun was just one star among billions, perhaps we are on the brink of another great revelation, that our universe is not unique, and that scattered across the infinite are countless other worlds, where untold stories continue to unfold. Perhaps, in one of those worlds, you are living a different version of your life. Or perhaps the real miracle is this, that this very version, this bed, this moment, this awareness, has emerged from among billions of possibilities. And now, the next step in our journey is to look into quantum physics and see how it shatters the limits of classical logic, opening wide the doors to multiple realities. Imagine a world where everything that exists, every atom, every particle, every thread of light, can be in several places at once. A world where reality isn't a straight line, but a tapestry of interwoven possibilities, waiting to be chosen by observation. That world exists. It is the quantum universe, and it is here that our journey in search of parallel lands finds one of its most solid foundations. Quantum physics emerged to explain the behavior of the subatomic world, and ended up revealing a universe stranger than any fiction. While classical physics describes a deterministic world, where causes lead to predictable effects, the quantum world operates under laws of probability, uncertainty, entanglement, and superposition. Instead of stating exactly what a particle does, physicists began using mathematical functions to describe what it couldn't do, and only when we observe the system does one of those outcomes become real. This idea became famous through the double-slit experiment, where particles like electrons are fired at a barrier with two openings. If no one observes the path of the electrons, they behave like waves, interfering with themselves and creating an interference pattern, as if they passed through both slits at the same time. But if we try to observe which slit the electron goes through, it behaves like a particle, choosing one path and making the interference pattern disappear. That means the very act of observing changes the outcome. For Danish physicist Niels Bohr, this phenomenon revealed a fundamental principle. There is no reality without observation. But for many, this answer seemed incomplete. And so, in 1957, Hugh Everett III proposed a bold solution. The wave function does not collapse. All possibilities come true, but in different universes. In other words, instead of the universe deciding which path the electron took, the cosmos splits, and in each reality, a different result unfolds. This is the so-called many worlds interpretation of quantum mechanics, perhaps the most radical and yet the most mathematically consistent model. According to it, at each quantum event, the universe branches out, creating copies of itself with small or large variations. If you flipped a coin and got heads, there's a universe where it landed tails. If you chose to listen to this audio now, there are versions of you who didn't, and all of them continue to exist, each evolving with its own story. At first, this idea was ridiculed. Everett died without recognition, but as physics and the philosophy of science advanced, the theory gained supporters. Today, names like Sean Carroll, Caltech, David Deutsch, Oxford, and Max Tegmark, MIT, openly support the plausibility of the quantum multiverse. The central argument is that Schrödinger's equation, which governs the evolution of quantum systems, does not require any collapse. The collapse is merely an illusion, born of our partial interaction with the system. And there's more. In modern experiments involving quantum entanglement, scientists have demonstrated that two particles can remain connected in such a way that an action on one instantly affects the other, even if they are separated by thousands of kilometers. This phenomenon, called non-locality, was confirmed in experiments that violated Bell's inequalities and earned the 2022 Nobel Prize in Physics for Aspect, Clauser, and Zeilinger. It suggests that, at some level, reality is unified beyond space and time, and that what happens in one point can instantly reflect elsewhere, as if all possible versions of a system are invisibly connected. But what does this mean for you now, lying under the veil of sleep? It means your consciousness, your choices, your paths may be unfolding within a multiverse of living possibilities. That every thought, every decision, opens new branches into realities we'll never perceive, but that exist. You are therefore one among infinite versions of you, each exploring an alternate version of this very life. And if that sounds too philosophical, it's worth remembering. Science doesn't deny strangeness. It measures it. The many worlds interpretation is a real solution to quantum paradoxes. Not fiction, but a possibility that arises from the mathematics itself. A solution that requires no hidden variables or mystical mysteries, only the courage to accept that reality is larger than what we can see. So, as you fall asleep, think about this. In one parallel world, sleep might have been replaced by a late-night coffee, in another by a conversation, in another by silence, and in all of them, you exist, a living constellation of possibilities, rippling through the vastness of a quantum cosmos. Imagine a universe made of music, but not the kind of music you hear with your ears, rather an invisible symphony, composed of vibrations so small and subtle that they shape everything that exists, from the light of stars to the matter in your body. This is the proposal of string theory, one of the most ambitious and intriguing attempts in modern physics to unify the universe under a single mathematical language. And in doing so, it offers more than just an explanation for particles. It opens conceptual portals to other universes, hidden realities, and dimensions that may exist beyond our perception. Throughout the 20th century, physics was split into two pillars: general relativity, which describes the cosmos on large scales, planets, stars, galaxies, and quantum mechanics, which governs particles at tiny scales. Both work extremely well, but they don't fit together. When we try to apply them simultaneously in extreme regions like black holes or the beginning of the Big Bang, the equations collapse. It's as if we had two perfect languages, but they are incompatible. String theory was born from the effort to solve this conflict. Instead of imagining that fundamental particles are zero-dimensional points, the theory proposes that everything in the universe is made of infinitesimal vibrating strings. These strings can be open or closed, and the way they vibrate determines the particle they manifest. An electron, a photon, a quark, all would be different vibration patterns of the same fundamental entity. But for this theory to work, there's a crucial detail. It requires more dimensions than we perceive. Our world has three spatial dimensions: height, width, and depth, and one time dimension. But string theory requires, depending on the version, 10 or even 11 dimensions. That's because strings can only vibrate freely in a more complex space, with directions that go beyond our daily experience. These extra dimensions are not visible because, according to the theory, they're compacted, rolled into tiny structures called Calabi-Yau manifolds, so small they're billions of times smaller than a proton. Imagine a sheet of paper rolled so tightly that from afar it looks like a straight line. That's how these extra dimensions behave, present yet imperceptible. And here's where the concept of parallel universes enters, because in a space with so many dimensions, it's possible that brains, three-dimensional membranes like ours, are floating in a larger space known as the bulk. On each of these brains, there could be a universe with its own physical laws, its own particles, its own history. Our universe would be just one such brain, and the others, inaccessible, invisible, but real, would be vibrating in parallel to ours, separated by fractions of millimeters in a dimension we can't reach. This model is explored in the so-called M theory, proposed by Edward Witten and other physicists in the 1990s as a unifying extension of the various versions of string theory. M theory suggests that strings, brains, and dimensions are all part of a single cosmic organism, one whose full nature we are still far from understanding. In scenarios like the ekpyrotic universe, two brain universes might even collide, generating a Big Bang at ours as the result of that cosmic interaction. The beauty of this model lies not only in its physics, but in the vision it offers of reality, a universe where we're not alone, not because there's alien life, but because there are other entire existences coexisting with us, separated only by a geometry we cannot perceive. And for you, now falling asleep, that idea might be strangely comforting, that perhaps beyond the stars, beyond time, there are other versions of reality where other forms of you are also falling asleep, dreaming, living. Although we don't yet have direct experimental proof of string theory or extra dimensions, scientific interest remains strong. Major collaborations, such as those at CERN, are investigating whether particles like the gravitons predicted by the theory might escape into other dimensions, causing subtle anomalies in particle collisions. And telescopes like the James Webb may indirectly offer clues about the shape of the universe and its origin, either supporting or challenging these models. In the end, string theory invites us to imagine the cosmos as a multidimensional symphony, where each universe is a note, each dimension an instrument, and every vibrating string composes the music of existence. As you breathe with your eyes closed, imagine yourself floating among those cosmic brains, gently gliding from one reality to another, listening to the primordial sound of strings vibrating since before time began. Imagine the universe as a foam, not a rigid, unchanging surface, but a living texture, constantly bubbling. Each bubble that forms, grows, and detaches is a universe, perhaps ours, perhaps another, perhaps trillions. This is the extraordinary vision suggested by the theory of eternal inflation, a model that completely redefines what we call the cosmos and leads us, with serenity and science, to a scenario where the multiverse is not merely possible, but inevitable. To understand this idea, we need to return to the moment just after the Big Bang, when the theory of cosmic inflation was first proposed by Alan Guth. According to him, the newborn universe underwent a violently accelerated expansion, an exponential growth that in less than a fraction of a second increased the size of the cosmos by trillions of times. This inflation helped solve mysteries such as the universe's homogeneity and its surprisingly flat geometry. And as strange as it sounds, the math works. Measurements of the cosmic microwave background, recorded by satellites like WIMAP and SCU and Planck, reinforce the foundations of this idea. But something even deeper emerges when we explore the consequences of inflation. Physicist Andre Linde, alongside Guth, realized that inflation might never completely stop. In some regions of space, it halts, giving rise to universes like ours. In others, it continues, creating new pockets, new bubbles, new worlds, and so on endlessly. This is eternal inflation, a process that never fully ends, turning the very act of existence into a cosmic machine for universe creation. Each bubble formed in this process expands on its own and begins to follow its own physical laws. Some may have different fundamental constants. Gravity might be weaker, light might travel slower, particles might combine in exotic ways. The vast majority of these universes could be sterile, uninhabitable, fleeting, but in a few, perhaps vanishingly rare, the conditions align just right as in our bubble. A universe where matter organizes, stars are born, and beings like you can contemplate these ideas before sleep. This model creates what scientists call the cosmic landscape, an infinity of realities, each one separated from the others by vast, unreachable expanses of inflating space. Since these bubbles expand faster than anything can travel, they are, for all practical purposes, causally isolated from one another. It's as if each universe lives out its own eternity, never encountering its neighbors. Visualizing this landscape may seem impossible, but the equations are there. Theories like string theory, with its abundance of possible solutions, estimated at around 50 viable configurations, align perfectly with eternal inflation, offering millions of ways for the laws of physics to manifest in each bubble. Each universe might correspond to one of those solutions. This panorama has been explored by physicists like Leonard Susskind and Raphael Bousso, who propose that the selection of our universe can be explained by the anthropic principle. Among all the bubbles, we perceive only the one where conditions allow the existence of observers, like us. It's a profound yet comforting thought, because among all possibilities, you are here, listening to this story, breathing slowly in a bubble that allows for life, for love, for consciousness. Perhaps it's coincidence, perhaps it's necessity, perhaps the universe, or the multiverse, is above all fertile in possibilities. And as you fall asleep, imagine yourself floating inside one of these bubbles, while thousands of others expand around you. Some collide, others drift apart. All contain stories we'll never hear, but they exist alive, vibrant, silent. And within them, versions of time, of matter, and of reality unfold like dreams. Eternal inflation not only transforms the universe into a living organism, it transforms the idea of existence into an infinite tapestry. And perhaps among all these bubbles, some contain other you, living other nights, making other choices. Close your eyes once more and imagine. Somewhere in the multiverse, perhaps trillions of light years away, or maybe just a breath away in a parallel reality, there exists another you, someone with your face, your name, your body, but who made different choices, who took a different path, who said yes when you said no. This isn't isolated science fiction fantasy. It's a plausible consequence of some of the most respected theories in contemporary physics, and the name for it is mirror universes. In the view of the quantum multiverse, initially proposed by Hugh Everett III in the 1950s, every time an event occurs with more than one possible outcome, the universe branches. Not symbolically, literally. New versions of the universe begin to coexist, each containing one of the possible consequences of that event. When you chose what to wear today, when you took a sip of water, when you decided to listen to this story to fall asleep, other versions of you made different choices, and all those versions continue to exist, evolving in parallel worlds. This is the heart of the many worlds interpretation of quantum mechanics. Instead of a wave function collapse reducing reality to a single version, it proposes that all possibilities occur, and that the cosmos is like a living tree, where each fork represents a new reality, a new path, a new version of you. This view is supported by physicists like Sean Carroll, Caltech, who says, quantum mechanics doesn't choose a result, it preserves them all. We just happen to live in one of the branches. But what if we go further? What if these alternate you are not only the result of specific decisions, but exist in universes with slightly different initial conditions, with divergent histories from the very beginning of time? This is where mirror universes come in, an idea grounded in both quantum interpretations and the symmetry principles of fundamental physics. Modern physics is obsessed with symmetry. It looks for patterns, repetitions, reflections. There are theories suggesting that for every particle, there exists a counterpart, a kind of reflection in the mirror of existence. This leads to the hypothesis that there may be a twin universe to ours, where everything is similar but not identical, where matter behaves in reverse or where the arrow of time flows backward. A mirror universe might contain galaxies, stars, planets, and copies of ourselves living in slightly altered conditions where chance and physics combined in another way. Within the frameworks of string theory and inflationary cosmology, these versions are not only possible, they are expected. If eternal inflation creates bubbles with random physical parameters, and if there are billions of such bubbles, then statistically there will be universes so similar to ours that we could hardly tell them apart. Eventually, there will even be almost identical universes, with versions of you listening to this same narration, perhaps with different words, perhaps with different thoughts, but essentially, you. Physicist Max Tegmark, in his classification of multiverse levels, calls this Level I and Level 2 multiverse. In Level 1, regions beyond our observable universe contain our duplicates simply because space is infinite and particle arrangements are finite. In Level 2, universes with different physical constants but still similar structure arise from cosmic inflation. In both cases, the existence of other yous is not just possible, it's inevitable, if we accept the premises of these theories. And what does this mean for you right now? Maybe nothing changes in your daily life, but on a deeper level, this idea touches something existential. You are not alone. There are other versions of you. In some worlds, you fulfilled every dream. In others, you made mistakes you never forgave. In others still, you live a life you never dared to imagine. And in all of them, you are real. This perspective is not a sentence to insignificance. On the contrary, it magnifies your presence in this world, in this moment, because among all the possible versions of you, this is the one that's here, now, breathing, awake, or almost asleep. That is a cosmic singularity, a monumental coincidence. You, exactly as you are, living exactly this moment. As you sleep, allow yourself to drift between those parallel realities, where versions of you walk different paths, where music plays at a different frequency, where reality reflects you, but not the same you. Relax. Take a deep breath. Now imagine that everything you know, the bed you're lying on, the sounds around you, the stars in the sky, even your body and your thoughts, is nothing more than a carefully programmed simulation, a perfect illusion, generated by codes, mathematical laws, patterns of information, a reality that, although it feels solid, is made only of projections. This idea doesn't come from science fiction films like The Matrix. It has deep roots in some of the most advanced frontiers of contemporary theoretical physics, and it leads us to one of the most intriguing concepts of our time, the universe as a hologram. The so-called simulation hypothesis gained notoriety in 2003 when philosopher Nick Bostrom from Oxford University published a paper suggesting that a technologically advanced civilization could, in theory, simulate entire realities, including self-aware consciousnesses, given enough computational power. If that's possible, then it would be more likely that we are inside one of these simulations rather than in the original reality. After all, if one real universe can generate billions of simulations, statistically, we'd be just one more coded instance. But this idea doesn't stand alone. Theoretical physics offers us an even more surprising hypothesis that the universe itself might be a hologram. This proposal arose from studies on black holes and the so-called information paradox, where physicists were trying to understand whether the information of an object that falls into a black hole is lost forever. In 1993, physicist Leonard Susskind de Souza and Nobel laureate Gerard 't Hooft proposed that information isn't lost, but instead encoded on the two event horizon facet of the black hole. This led to what we now call the holographic principle. The holographic principle suggests that everything happening within a three-dimensional volume can be described by information encoded on a two-dimensional surface surrounding it, just like a hologram, where a 3D image is generated from a 2D pattern. This theory was reinforced in the years that followed by physicist Juan Maldacena, who in 1997 demonstrated a precise correspondence between a gravitational theory in 5 dimensions and a quantum theory without gravity in 4 dimensions. This model, known as ADS-CFT correspondence, became one of the foundations of modern theoretical physics and carries profound implications. Our 3-dimensional universe, including time, might be a projection of a more fundamental reality encoded in a lower dimension. This view completely changes our relationship with the concept of reality. We don't live in absolute space, but in an emergent reality, built from pure information, where space and time are secondary consequences, not fundamental truths. For many scientists like Seth Lloydus from MIT, the universe can be interpreted as a quantum processor, a giant information processing machine where each interaction between particles is a calculation, each atom is a bit, each phenomenon is a data process. And what does this have to do with the multiverse? Everything. Because if the universe is a simulation, then there may be multiple simulations, multiple versions, multiple layers of reality, each with its own physical laws, its own time, its own observers. This connects the simulation hypothesis to the idea of parallel universes. And if the universe is a hologram, then other surfaces may contain other projected realities, each one vibrating at its own rhythm with its own code. It's as if we were inside a massive cosmic operating system, where realities are loaded, processed, and perhaps even layered, like open windows on a computer. And maybe consciousness is the cursor, the bridge that navigates between these windows. This could help explain phenomena like entanglement, superposition, or even déjà vu, echoes from other versions of ourselves in other instances of the same code. You might find all this too abstract. But when we observe that the universe is mathematical, that its foundations are described by elegant and symmetrical equations, and that these equations generate everything we know, an inevitable question arises. Are we in the original reality, or in a well-crafted projection? This idea might sound cold, but there is poetic beauty in it. Because even in a simulation, even in a hologram, love, sleep, dreams, and thoughts still exist, as vibration patterns, as code structures, as the dance of information. And perhaps in the silence of night, you can feel that invisible texture, that digital backdrop of the cosmos, where realities are generated like gentle waves spreading across eternity. As you fall asleep, think about this. You are part of an equation, a living line of code, dancing between probabilities. And even so, you feel, you breathe, you dream. And that might be what makes it all real. Lie down gently. Let your body sink into the mattress. Your thoughts slow down and your imagination expand. Now visualize this. You are in a room. You can perceive its length, its width, its height. 3 dimensions. But what if there are more directions in space, hidden from your senses, curled up, compressed on scales so small that they go unnoticed by all of humanity? This is the idea of hidden dimensions, a concept that, though invisible, may hold the keys to multiple parallel realities and to the very structure of the multiverse. In classical physics, we learn that we live in a universe with 3 spatial dimensions and 1 temporal dimension. But modern physics invites us to go further. Theories such as string theory, Hawley's M theory, and some models derived from the quantum gravity require the existence of additional dimensions, not out of whim, but because without them, the equations simply do not work. These extra dimensions are not out there in deep space. They're everywhere, around you, inside you, within each atom, just invisible. These extra dimensions are compactified as if they were tiny rolls of paper so tightly curled that we cannot even detect them. The math that describes this relies on structures called Calabi-Yau manifolds, complex geometric objects that hold 6 or 7 additional dimensions beyond the ones we know. If these dimensions exist, then every point in our 3D space contains a much deeper reality, where the strings of string theory vibrate and determine the behavior of fundamental particles. But what does this have to do with parallel worlds? Everything. Because if there are more directions to reality, then it's possible that there are entire worlds, fully formed, completely hidden from our perception, existing in other layers and phases of space-time. These hidden dimensions could house overlapping universes that share the same physical space but do not directly interact with ours, like radio stations transmitting on different frequencies. You could be in the same place as another version of yourself and never see each other. In some models, like those proposed by physicists Lisa Randall and Raman Sundram, these extra dimensions not only exist, but could be large and warped, making it possible for forces like gravity to unleak into other universes. This might explain why gravity is so much weaker than the other fundamental forces, perhaps because part of its energy is being diverted into other dimensions, into other worlds. Moreover, if these hidden dimensions are real, then phenomena that today seem inexplicable, like dark matter, could actually be the effects of parallel universes colliding or interacting with ours in subtle ways. Dark matter makes up about 27% of the universe, but it has never been directly observed, only inferred through its gravitational influence. Some theorists suggest that what we perceive as dark matter may be the shadow of other worlds present here, but hidden between dimensions. These ideas are not mere speculation. They inspire real experiments. The Large Hadron Collider, LHC, the world's largest particle accelerator, conducts experiments trying to detect micro-black holes, extra-dimensional particles, and signals from hidden brains. So far, results have not confirmed the existence of extra dimensions, but they haven't ruled them out either, and physics keeps searching. Now think about this. You live in 3 dimensions, but your body, your mind, your existence may be immersed in a much broader reality. When you sleep, you don't just rest. You surrender to the invisible, to what lies beyond control. Perhaps dreams dwell in these hidden dimensions. Perhaps it's there that versions of you walk paths you've never taken. Perhaps love, fear, longing are echoes of dimensions that touch ours without us noticing. As your breathing deepens and sleep approaches, visualize the dimensions as veils, delicate layers dancing around your body, concealing entire realities. In one of those layers, another you is also lying down, in peace, in silence, sleeping in a universe made of possibilities. Imagine a point in space where time stops, light vanishes, and the very structure of reality folds in on itself. A place where the laws of physics as we know them cease to function. This place exists, and it carries a name filled with mystery, fear, and fascination: black hole. But what if beyond being graves for matter and light, black holes are actually portals, dimensional doorways, shortcuts to other worlds? Some say yes, and some search through equations and telescopes for the evidence. Black holes arise naturally from the equations of Albert Einstein's general relativity, published in 1915. They are regions of space where gravity is so intense that nothing, absolutely nothing, not even light, can escape. When a massive star exhausts its fuel, it may collapse under its own weight, forming a singularity, a point of infinite density surrounded by an SAS event horizon, the boundary beyond which there is no return. For decades, black holes were treated as theoretical curiosities, but today we know they are real. We've observed their gravitational effects, their violent collisions, like those detected by the LIGO Observatory, which recorded gravitational waves from black hole mergers, and more recently, we've even captured their shadows. In 2019, the High Event Horizon Telescope revealed the iconic image of the black hole at the center of galaxy M87. But behind that quiet, dark appearance lies an even more unsettling possibility. Black holes might be portals to other universes. This idea emerges from several branches of theoretical physics. One involves the so-called wormholes, or Einstein-Rosen bridges, predicted as exact solutions to Einstein's equations. A wormhole is like a tunnel through space-time, connecting two distant points, or even two separate universes. In theory, it might be possible to travel through this tunnel and emerge in another time, another galaxy, or another reality. Although we have no empirical evidence yet, the math suggests that, under certain conditions, wormholes could remain stable long enough to allow passage. Other models, such as the one proposed by Lee Smolin, suggest that every black hole could give birth to a new universe. This is the idea of BDU, cosmological natural selection, where our own universe may have emerged from the interior of a black hole within a larger parent universe. In this scenario, space inside the black hole expands, forming a separate universe that is causally disconnected from its origin. Each new universe might have slightly different physical parameters, and those that produce more black holes become more common over time, like a cosmic form of natural selection. Then there's the intriguing possibility that the information swallowed by a black hole isn't destroyed, but instead reprojected elsewhere. This debate, known as the black hole information paradox, has engaged physicists like Stephen Hawking, Leonard Susskind, and Gerard Houghton for decades. The most accepted resolution today suggests that the information is preserved on the surface of the event horizon, which, interestingly, supports the holographic principle, where all of 3D reality is encoded on a 2D surface. But what if some of that information escapes to another universe? What if the inside of a black hole is an exit door, a transition between realms, where the matter and energy that enter don't disappear, but reboot in a brand new cosmos? This vision inspires not only science, but also the imagination. Imagine being drawn into a black hole. First, the light bends, then time slows, space distorts, and then, instead of an end, a beginning, another universe, other stars, another version of reality. As you fall asleep, picture the black hole not as destruction, but as passage, a silent capsule holding within it the secret of cosmic multiplicity. Every black hole in the sky might be the cradle of a new universe, vibrating in a dimension where the rules are different, but the essence, the possibility of existence, remains. And in this very moment, perhaps somewhere in a distant fold of space-time, a new universe is being born, in the dark, in silence, like you now drifting into sleep. Relax, breathe slowly, and imagine a universe where time flows more slowly, where gravity is 10 times stronger, where light travels at a different speed, where the atom as we know it cannot even exist. Now imagine billions of such universes, each with its own set of rules, its own physical laws. This is the scenario proposed by many versions of the multiverse, not just other worlds, but other realities built on entirely different foundations from ours. In physics, we call fundamental constants the values that define how nature behaves: the speed of light in a vacuum, Planck's constant, the charge of the electron, the gravitational constant, and others. These constants were not chosen by anyone. They simply are. But the deeper question is, what if they were different? What if there were other universes where those constants had slightly, or radically, different values? The answer is unsettling. The vast majority of these universes would be sterile, uninhabitable, perhaps even unknowable. The physicist Martin Rees-T, in his book Just Six Numbers, shows how small changes in some of these values would render life, or even matter, impossible. If the strong nuclear force were just a little weaker, protons wouldn't bind to form nuclei. If it were stronger, the universe might have collapsed before stars could form. If the cosmological constant were slightly larger, the universe would have expanded too quickly for galaxies to emerge. If it were smaller, everything would have collapsed again in an instant. The balance is so precise that many scientists wonder whether there's a deeper explanation behind this cosmic fine-tuning. That's where the idea of a landscape of universes comes in, proposed by theorists like Leonard Susskind. In string theory, there are around 10,500 possible solutions to the equations that describe the vacuum's energy states, each with its own physical laws. Each of these solutions could correspond to a different universe. This near-infinite set of possibilities is known as the landscape, a cosmic terrain where each valley represents a universe with distinct laws. But if there are so many possible universes, why do we live in this one with these particular laws? One possible answer is the anthropic principle. Among the trillions of possible universes, we can only exist in those that allow for the presence of conscious beings. In other words, it's not that this universe was made for us, we simply emerged in the one that makes our existence possible. Now let your mind wander. In some universe, gravity might be so strong that mountains rise no higher than a few centimeters. In another, light may travel more slowly, altering the very perception of time. In yet another, life might be based on structures that here would be unstable, or even invisible. Perhaps in one of those worlds, sentient beings evolved in liquid atmospheres or plasma clouds, or in silent crystalline networks. What's impossible here might be inevitable there. And if there are universes with such different laws, what would happen if they touched ours? Some hypotheses suggest that collisions between bubble universes during eternal inflation could leave marks, subtle disturbances in the cosmic microwave background, like scars from reality meeting reality. So far, none of these signs have been confirmed, but missions like the Planck satellite continue analyzing data in search of these echoes of the multiverse. But perhaps we will never observe these universes directly. Perhaps they will remain forever beyond our causal reach. And yet, physics invites us to contemplate them, because understanding what could be is part of what we are. To imagine physical laws unlike our own is in itself a kind of consciousness expansion, a way to free the mind from the walls of the known. As you breathe, perhaps slowly drifting towards sleep, think of this. In this universe, you are made of carbon, electrons, time and gravity. But in another, you might be made of something else, or be something else, or not be at all. And yet, among all the possibilities, you are here, in this moment, in this world, where physics allows dreaming, and dreaming allows everything. Close your eyes. Inhale slowly. Feel your thoughts slow down like gentle waves retreating from the shore. Now imagine that your mind, the part of you that says I, is not confined to this universe. What if somehow it could touch other realities, perceive traces of other worlds, access, even briefly, other planes of existence where alternate versions of you continue to live? Here science and consciousness intertwine, opening a portal not just to the cosmos, but to the deepest interior of the self. Modern physics has already shown that consciousness is a complex phenomenon, but still not fully understood. Despite all advances in neuroscience, the origin of consciousness remains one of science's greatest mysteries. We know there's a relationship between brain activity and mental states. But how does subjective experience arise? How does raw matter generate thought, emotion, perception? This is what we call the hard problem of consciousness, a term coined by philosopher David Chalmers of New York University. Some theorists suggest that consciousness is not a byproduct of the brain, but a more fundamental entity, perhaps as essential as space, time, and matter. This echoes ancient philosophical traditions, from Vedanta to the German idealism, and aligns with modern models like the orchestrated objective reduction theory, OR, proposed by physicist and Nobel laureate Roger Penrose and anesthesiologist Stuart Hameroff. This theory suggests that consciousness may arise from quantum processes within the microtubules of brain cells, connecting the mind to universal quantum phenomena. And if the mind is connected to this deep quantum layer, then in theory, it might access realities beyond normal sensory experience. This leads us to ask, could dreams, déjà vu, or sudden insights be fragments of experiences in other realities? Could it be that while asleep, the mind tunes into different versions of the self? The idea that consciousness transcends the brain also appears in a hypothesis called panpsychism, where consciousness is seen as a fundamental feature of the universe, like mass or electric charge. Scientists like Georg Christoph Kocher and philosophers like Philip Goffer argue that the universe itself may be, in some degree, conscious, and if that's true, then perhaps the mind is the bridge between multiverses. There's also speculation that in altered states of consciousness, deep meditation, lucid dreaming, near-death experiences, perception might break through the filter of ordinary reality, allowing flashes of other versions of the self, of other timelines, of other existences. In a study published in Frontiers in Psychology, researchers observed that non-ordinary mental states activate more chaotic, freer brain patterns, as if the brain is trying to access something beyond the current model of reality. Even without definitive proof, this idea resonates with common human experiences. Who hasn't felt they've been to a place they never visited, or dreamt of a life that isn't theirs, but feels strangely familiar? Could it be that in those moments we are tuning into other versions of ourselves, living in parallel worlds? Of course, science remains cautious. We cannot yet confirm that the mind accesses alternate realities, but the multiverse, with its infinite worlds, and consciousness, with its unfathomable depths, remain the two greatest mysteries of the known universe. And perhaps it's no coincidence that exploring one often leads us straight into the other. As you relax, think about this. Your mind is more than thoughts. It is a vibrating field, perhaps interconnected with the very fabric of the cosmos. And perhaps as you fall asleep, it softly glides between layers of reality, visiting parallel lands where other stories are being lived by other versions of you, who also dream, also feel, also search. Let your body rest. Feel your heartbeat slowing down. Time begins to decelerate around you. You close your eyes, and without moving, you begin to travel. Now, imagine that in some other universe, time doesn't flow as it does here. Imagine it running backwards. Mornings come after nights. Causes follow effects. The past hasn't happened yet, and the future has already gone by. As strange as it sounds, this isn't just fiction. In some aspects, it is mathematically allowed by the laws of physics. In our universe, we live immersed in what we call the arrow of time. It pushes us from past to future on a continuous line that never turns back. We feel time passing. We see ice melt, but never water freeze spontaneously. People age. Waves break on the sand. Smoke rises. But why? What makes time flow in only one direction? According to the second law of thermodynamics, in any isolated system, entropy, that is, disorder, tends to increase. This is what gives time its direction. The past is a state of lower entropy, and the future is more disordered. But in the fundamental equations of physics, those that govern quantum mechanics or general relativity, time is reversible. The equations work just as well forwards or backwards. There's nothing in them that forbids the universe from evolving in reverse. This led scientists and cosmologists to speculate, could there be universes where the arrow of time points in the opposite direction? Universes where entropy decreases with the passing of time, where life begins in chaos and moves toward perfect simplicity? In 2014, physicists Julian Barber, Tim Kozlowski, and Flavio Mercati proposed a model in which time is not a line, but a symmetric curve. In a paper published in Physical Review Letters, they suggested that the universe may have emerged from a point of minimal entropy, and that the arrow of time unfolds in both directions at once. In one, entropy increases, as it does in our experience. In the other, it also increases, but in the reverse direction. For the inhabitants of that universe, everything would feel normal, but to us they'd seem to live from future to past. This theory aligns with models of twin universes born during the Big Bang. In this scenario, when the universe was created, it may have split into two branches, one where time flows forward as we know, and one where everything happens in reverse. This concept is also explored by cosmologists Sean Carroll and Jennifer Chen, who study the origin of the universe's initial entropy and the possible symmetries between realities. And what does this mean for us? Perhaps that time is not a universal entity, but a local experience. In some worlds, it may move forward, in others, backward. In others still, it might be cyclic or layered, or even non-existent. There are theories, such as those by Barber, that claim time is merely an illusion, a construct emerging from change, that only the now exists, and the past and future are mental creations. In quantum mechanics, the idea of reversibility also exists. In some interpretations, wave function collapse could, under specific conditions, reverse a system's temporal flow, though this has never been observed on a macroscopic scale. And in the realm of black holes, time near the event horizon slows down until it stops entirely, suggesting that time can behave in extreme ways depending on its physical environment. As you listen, a curious thought may arise. Could your dreams be echoes from other arrows of time? Could memories that don't belong to this world, visions of something yet to happen, be fragments of consciousness navigating realities with different chronologies? As you fall asleep, allow yourself to let go of linearity. Think of time not as a track, but as a river, one that can branch, reverse, evaporate, and fall again as rain. In some other universe, someone like you may be reliving today before it even happens, and for that version of you, the now is always the beginning, never the end. Let yourself be carried by this silence. Your mind is calm, open, gently drifting through questions that seem to have no answer. And maybe it's precisely this absence of certainty that makes the universe so fascinating. After all, when we speak of the multiverse, of parallel realities, mirror worlds, and wormholes, one question inevitably arises. Is there evidence? Can we prove it? And more importantly, what are the limits of science itself when faced with such a vast and for now invisible domain? The idea of a multiverse is for now a scientific hypothesis, powerful, elegant, coherent, with many mathematical theories, but still unconfirmed by experimental data. And that's a key point. Science, unlike belief, demands testing, repetition, falsifiability. For something to be scientifically valid, it must generate predictions that can be compared with real-world data. And here, the multiverse finds itself in a unique position. It emerges naturally from testable theories, yet its existence might never be directly accessible. Let's take a closer look. The theory of cosmic inflation, for example, is strongly supported by observations of the cosmic microwave background, CMB, the afterglow of the Big Bang. Satellites like WMAP and Planck, by measuring this radiation with extraordinary precision, confirmed many of inflation's predictions: the homogeneity of the universe, its isotropy, and the small density fluctuations. And inflation, in turn, predicts that new bubble universes may continuously emerge in a process called eternal inflation. That means the multiverse isn't a mystical invention, it's a theoretical implication. Likewise, string theory, which aims to unify all fundamental forces, predicts an almost infinite number of possible solutions for the state of the universe, each with different physical laws, different fundamental constants. This vast set of possibilities is known as the S-string theory landscape, and suggests that our universe might be just one among trillions of possibilities. But directly testing those versions is, for now, beyond our technological reach. Still, scientists search for indirect signs. One area of study involves looking for anomalies in the cosmic microwave background that could be scars from collisions with other universes, as if bubbles of reality had touched in the distant past. So far, these searches haven't found definitive evidence, but they continue. Another line of research seeks to detect particles that might leak into other dimensions, such as extra-dimensional gravitons, in particle accelerator experiments like those at the Large Hadron Collider, LHC. So far, no conclusive detection. Physicist Stephen Hawking, in his later work, proposed a refined version of eternal inflation where the existence of a multiverse could be statistically calculated, based on the properties observed in our own universe. For him, the multiverse might not be directly observable, but it could leave probabilistic signatures reflected in how our cosmos behaves. But what if we never prove it? Would science be defeated? Not at all, because science isn't a collection of absolute truths. It's a tool, the best we have, for investigating, modeling, and understanding reality, and part of that journey is facing its own boundaries. Karl Popper said a theory is scientific only if it's falsifiable. Others, like Thomas Kuhn-Hsiu, argued that science advances through paradigms, and sometimes what seems untestable today becomes observable tomorrow. with new tools, new eyes, new frameworks. Thus, the multiverse currently lives at the edge of the possible and the observable. Mathematics supports it, logic allows it, physics suggests it, but the data is still to come. And maybe even if we never see another universe, the fact that we can conceive it, clearly and coherently, is already a sign of science expanding. As Carl Sagan once said, "The absence of evidence is not evidence of absence." As you rest, wrapped in silence, think about this. You are part of a universe that looks at itself and wonders if it is alone. And that question, in itself, is a miracle, because only a universe that contains consciousness can long to find others. Close your eyes once more. Breathe in slowly and deeply. Now allow yourself to feel the weightlessness of the question that has guided us for so many hours. What if all of this is real? What if every theory, every universe, every dimension we've explored isn't just an idea, but a fact still invisible, distant, unreachable, but that exists like islands in the fog, waiting only for the right light to reveal their shape? What changes within us when we accept that the universe might be far vaster than we ever imagined? Throughout the history of science, humanity has expanded its view of reality. We discovered that Earth is not the center of the cosmos, that the sun is only one among billions of stars, that our galaxy is just one of trillions, and now perhaps we are on the edge of another great expansion of consciousness, realizing that our universe may itself be just a grain of sand on an infinite beach of realities. Accepting this possibility can be unsettling. It may feel like we've lost our special place, but if we look closely, the effect is the opposite, because the more immense the cosmos reveals itself to be, the more precious becomes the simple fact of being here, now, conscious, breathing. Among trillions of possible universes, we emerged in this one, with these physical laws, these stars, this planet, this story. That doesn't diminish life, it makes it singular. And if there are other universes, with other versions of you, other lives, other choices, that does not undo the importance of what you are living right now. On the contrary, it highlights the uniqueness of the now, because among all the possible branches, among all the bifurcations of time and space, this moment is unrepeatable. There is also a comforting side to this idea. The multiverse doesn't have to be frightening. It can be seen as an infinite field of possibilities, where everything that could have been already was, where dreams that didn't come true here perhaps blossomed elsewhere, where words left unsaid, decisions not made, paths not taken, found space to unfold in other realities. And even if we never touch those worlds, maybe they touch us, softly, like echoes, like intuitions, like dreams. In philosophy, this idea touches on ontological plurality, the understanding that existence can take many forms, planes, and expressions. In spirituality, it echoes the belief that the human being is not limited to the physical, but manifests in layers. In poetry, it's an invitation to awe, to live in a world that may contain all worlds, a universe that sings with infinite voices, and one of them is yours. And if tomorrow we were to discover with scientific certainty that the multiverse is real, what would actually change in your daily life? Perhaps very little. You would still wake up, work, love, dream, as always, but deep down, knowing that all this is part of something greater could change how you exist in the world. It might bring humility, it might bring gratitude, it might bring peace. As sleep fully arrives, quiet as galaxies dancing in the dark, think of this. You are made of atoms forged in stars, animated by thoughts that defy space and time, surrounded by possibilities no telescope could ever fully capture. And even if infinite universes exist, even if everything repeats in endless variations, the version you are living now is unique. It is sacred. It is yours. Good night, traveler of the cosmos. May your dreams carry you even farther than physics has ever imagined.